Next, our portion is types of overlapping and nature of covalent bonds. That means, on the basis of orbital overlapping, the bonds are mainly classified into, that means, covalent bonds are mainly classified into two types. These orbitals are come closer to each other, that means they overlap to form a particular bond. On the basis of the orbital overlapping, covalent bonds are classified into two types. First one is sigma bond, denoted by the symbol like this, sigma bond. This type of covalent bond is formed by the head-on overlapping of atomic orbitals along the internuclear axis. Head-on overlapping or end-to-end overlapping of the atomic orbitals along the internuclear axis, then we get a sigma bond. This is called head-on overlap or axial overlap because this is head-on overlapping or internuclear axis. These atomic orbitals are overlapped, so this is otherwise known as axial overlap. These overlapping are of three types. First one is SS overlapping. In this overlapping, there is an overlap of two half-filled s orbitals along the internuclear axis. Listen here, that is, this is one s orbital, half-filled s orbital of one atom, and this is half-filled s orbital of another atom. Then these are come closer to each other, then they become overlap. Here, this overlapping is known as SS overlapping. That is, one s orbital overlap with another s orbital. This is known as orbital overlapping. You can see here. So this type of overlapping is known as SS overlapping. These are overlap through the internuclear axis. This is the axis, x-axis. Through this they come closer and overlap here. So this type of overlapping is known as SS overlapping. Then the next one is SP overlapping. Then what do you mean by SP overlapping? In this, there is an overlap of half-filled s orbital of one atom and half-filled p orbital of another atom along the internuclear axis. This is the axis. Through this axis, this s orbital and p orbital come closer to each other and they become overlap here. So this type of overlapping is known as SP overlapping. Next one is PP overlapping. In this, there is an overlap of half-filled p orbital of one atom and half-filled p orbital of another atom along the internuclear axis. Listen, p orbital, dumbbell shape, come closer to another p orbital, dumbbell shape. Through internuclear axis, they come closer to each other and they become overlap. So this type of overlapping is known as PP overlapping. So sigma bonds are formed by mainly SS overlapping, SP overlapping and PP overlapping. Then the next type of covalent bond formed by the orbital overlapping is pi bond. Pi bond, or denoted by the symbol this pi. This type of covalent bond is formed by the sidewise overlapping of atomic orbitals. So that is a p orbital of one atom and this is the p orbital of another atom. They come closer to each other not through internuclear axis but they overlap sidewisely. Through this side of these lobes they overlap. So this is known as sidewise overlapping of atomic orbitals are known as pi bond. So here this one p orbital, another p orbital overlap sidewisely, then we get PP overlapping. So sigma bonds are formed by the axial overlapping of atomic orbitals and pi bonds are formed by the sidewise overlapping of the atomic orbitals. Then strength of sigma bond and pi bond. So which type of overlapping is more stronger? Can you say sigma bond or pi bond? Which is more stronger? Yes, sigma bond is more stronger than pi bond because in sigma bond the extent of overlapping is more compared to pi bond. Here the extent of overlapping can be maximum. They can overlap more and more, but here this only this extent they can overlap. So the sigma bonds are more stronger than pi bonds because the extent of overlapping is more in sigma bond compared to pi bonds.
Hybridization is a phenomenon of mixing of atomic orbitals of different shape, size, and energy to form new equivalent orbitals of the same shape, size, and energy. Understanding hybridization by the daily life example. Suppose I want to make tea. So the ingredients needed to make tea are water, sugar, black tea, and the milk. When I boil all these two ingredients together, having the different texture and color, so I get tea. And every drop of the tea having the same color, taste, and smell. So the ingredients of the tea are like the atomic orbitals, whereas the tea is an example of hybrid orbitals. The shapes of the atomic orbitals. S orbital is spherical in shape, whereas the p orbitals are dumbbell shaped. They are also having the different energies, but when we mix these orbitals together, we get the hybrid orbitals having the same shape, size, and energy. These atomic orbitals are just like the ingredients of the tea, which are totally different from one another, whereas the hybrid orbitals are identical to one another.
So, hybridization is the process of intermixing of atomic orbitals of comparable energies and different shapes to form equal energy and identical shape hybrid orbitals. Hybridization is a process of intermixing of atomic orbitals to form hybrid orbitals. Here, the number of atomic orbitals combined are equals to the number of hybrid orbitals produced. For example, one s and one p orbitals are intermixed, then we get two equal energy and identical shape sp hybrid orbitals, two sp hybrid orbitals. Then the characteristics of hybridization. First one, hybrid orbitals always have equivalent energy and shape. The hybrid orbitals form stable bonds than unhybridized orbitals. Next, the hybrid orbitals are directed in space to avoid repulsion between the electron pairs. Thus, the type of hybridization indicate the geometry of the molecule. So, we know the hybridization, then we can identify the shape of the molecule. Then the types of hybridization. First one, sp hybridization. In this hybridization, the mixing of one s and one p orbital occurs, which resulting in the formation of two equal energy sp hybrid orbitals. S and p combine to form sp hybrid orbitals, which are two in numbers. Each sp hybrid orbitals have 50% s character and 50% p character, equal amount of s character and equal amount of p character for sp hybridization. The sp hybrid orbitals are linear in shape and lie in the same line in an angle of 180 degree from each other. You can see in the figure when one s and one p orbital combine to form two sp hybrid orbitals. One is this one sp and other is sp hybrid orbitals. These are arranged in a line, so this having linear shape with the angle 180 degree. Example for sp hybridization. Example beryllium chloride. For find out the hybridization, first you should find out the central atom. Here the central atom is beryllium, symbol beryllium, atomic number 4. Then the ground state electronic configuration you write 1s2, 2s2. Then the orbital diagram method is 1s2, 2s2. 2p orbitals are there, you know. The principal quantum number 2, main shell is 2, then 2 subshells are there, 2s and 2p. 2p is there, but there is no electrons, it is vacant. P orbitals 3 possible orientation, 2px, 2py, 2pz. Then the chlorine atoms are coming, then the beryllium atom become excited. So beryllium excited state or simply ES, ground state simply GS, and beryllium excited state simply ES. Then in the excited state, outermost shell paired electron, one electron jump to the higher energy level 2p. Then here two atomic orbitals with unpaired electrons. These atomic orbitals share the one electron of each chlorine atom to form beryllium chlorine single bond. So here the unpaired electron containing two atomic orbitals are mixed up to form one s orbital and one p orbitals are mixed up to form sp hybrid orbitals. This is one sp hybrid orbital, this is another sp hybrid orbital with angle 180 degree and linear shape. So note the point, sp hybrid orbitals are having linear shape. Then each of these sp orbitals overlap axially with half-filled 3p orbital of chlorine atom to form two beryllium chlorine single bond. Next one is sp2 hybridization. From this we can say 1s and 2p orbitals are mixed up to form 3 equivalent sp2 hybridized orbitals, because 1s and 2p total 1 plus 2 3. 3 equivalent sp2 hybridized orbitals. The 3 sp2 hybridized orbitals are directed towards the corners of a trigonal planar structure at an angle of 120 degree from each other. Trigonal planar shape, 1 sp2, 1 sp2, 1 sp2. 3 sp2 hybrid orbitals are arranged in a trigonal planar shape with angle 120 degree. These hybrid orbitals have 33% S character and 67% of P character. Example, boron trichloride, BCl3. So first you should write the boron atom in the ground state, normal electronic configuration 1s2, 2s2, 2p1. Then their orbital diagram method is 1s2, 2s2, 2p, 1 electron is only present. Then beryllium in the excited state, the outermost shell electron only excited. Then already one electron is here. From the outermost shell paired electron, one electron jump to the 2p level. Then here these unpaired electron containing orbitals are mixed up. Then 1s and 2p atomic orbitals are mixed up to form sp2 hybridized orbital. These three sp2 hybrid orbitals are oriented in a trigonal planar arrangement and overlap with a p orbital of chlorine atom to form 3 boron chlorine sigma bond. This is boron. Then 3 sp2 hybrid orbitals. These 3 sp2 hybrid orbitals, these are axially overlap with the p orbital of one chlorine atom, one chlorine atom, one chlorine atom to form 3 boron chlorine single bond. Then the next type of hybridization is sp3 hybridization. This involves the mixing up of 1s and 3p atomic orbitals of an atom to form 4 sp3 hybrid orbitals. 1s and 3p, total 1 plus 3, 4. 4 hybrid orbitals. Each sp3 hybrid orbitals has 25% s character and 75% p character. Then total 100, 25% s character and 75% p character. The 4 sp3 hybrid orbitals are directed towards the four corners of a tetrahedron with an angle of 109.5 degree. So, sp3 hybrid orbitals having shape tetrahedral shape. So, sp hybrid orbitals linear shape, sp2 with the trigonal planar shape, sp3 with the tetrahedral shape. Example, methane, CH4. First, you should write the central atom carbon, atomic number 6. In the ground state, electronic configuration is 1s2, 2s2, 2p2. Then the orbital diagram method is the electronic configuration 1s2, 2 electrons, 2s2, 2 electrons, 2p consist of 2 electrons. Then the excited state carbon, the electronic configuration is 1s2. This is the inner electron, so do not take part in hybridization. So 2s outermost shell, 1 electron jump to 2p level. Then here 1s and 3p orbitals are mixed up to form sp3 hybrid orbitals. These are 4 hybrid orbitals are produced. 1, 2, 3, 4 hybrid orbitals are produced. These are arranged on sp3, 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 sp3. These are arranged in the corners of a tetrahedron with the angle 109.5 degrees. 4 sp3 hybrid orbitals overlap with the 4 hydrogen atoms, 1s orbital of hydrogen atom to form 4 carbon hydrogen single bond. This is the types of hybridization involving s and p orbitals.